Okay, guys, we'll get started. Today, thank you guys all for coming. So this is just one of our weekly or our monthly user group meetings. Today we're going to talk a little bit about some of the upcoming expansions here at Niagara, as well as some of the money as part of the ISID funding across the different sites of the other national sites. This is just a quick overview of some of the hardware we're getting here and how it'll affect available resources and that type of thing. We have some of this hardware. It's not in place yet. We expect most of it should be up and running after Christmas, but definitely for the next rack year. But anyway, so just a quick overview. So SciNet, we host equipment here for Compute Canada. It's an NIAGARA system, along with some money from Compute Canada, Compute Ontario. We also host equipment for SOSIP, so previously the Blue Gene, the SGC system. And that's relevant here is because part of this expansion is expanding Niagara from Compute Canada money, but we're also, as part of SOSIP's refresh, they're combining in this resource as well. And so now we're combining those resources. So there'll be a shared resource, but not completely shared different systems. And I'll talk about that specifically here too. So just in this past, I guess, August, they announced ISID, so this is the Industry Development Canada, basically. They're reforming how the computing resources in Canada are funded for. Traditionally, for the last, many years, they've come from CFI. They're restructuring how that's all going to be together, and without getting into the whole details, this DRIs, or Digital Research Infrastructure. They've made a plan to merge kind of Compute Canada, some data management and research software sort of under one big umbrella. And there's this sort of order 570 million over the next 5 years. Specifically to that, 145 has been set for Canary, that's networking. Then there's sort of this 375 for this new org. And this is supposed to replace sort of Compute Canada and these other structures, but that's sort of under development. That sort of will take a few years to get sorted out, but there will be money for that. But there was a recognition as there was a need to expand the existing systems just because there's such a high demand. Right now. And so part of that was this immediate $50 million to add to the existing resources just as they are right now. So the 5 sites that you're familiar with, Graham, Cedar, Beluga, Arbutus, and Niagara, that are sort of, had relatively recently upgraded new equipment in the last couple of years. There was a calls put out, and for various reasons, there was various expansions done on each of them. So Graham's getting a relatively small CPU expansion. Cedar is getting a fairly large CPU and GPU expansion. Those are all happening right now. Beluga, that system will be another year later because they're building a new data center, but they're expanding this there well. The cloud storage is building also. And then also Niagara, we're getting a relatively small expansion of CPU. And then a new feature that we haven't had recently is we're also getting a GPU cluster. As I mentioned earlier, along with this money, SOSIP is also in the middle of a renewal too of their hardware. The Blue Gene was shut down this summer, and they right now at SciNet they only have a slightly older, smaller Power 8 GPU cluster. So there are new hardware requirements for GPU and CPU. So since we're timing this expansion, we're putting those together, and so we'll end up with a larger resource, but it'll be shared for those. So any of you who right now are in the camp where you have a SOSIP, your supervisor has a SOSIP allocation and a Compute Canada allocation. You're using 2 different resources. Under the new system, it'll actually all be the same thing. You just have 2 different accounting groups, but it will actually all be part of the same system. So we'll have less systems, but larger single systems. So it should make some of that management and file data management and account management a little more consistent for us and for the users, because most of those researchers have a hat in both camps, so it only makes sense. So just to review, the original Niagara system, when it was upgraded, it's, as most of you use right now, it's 1,500 of these Intel Skylake nodes. We're about 60,000 cores, a little higher than that. We had some contributed. Main features are it's InfiniBand EDR and this Dragonfly, so it's really high performant network. Backed by a fairly decent file system, about 10 petabytes right now, around 9, I think. So that's their scratch home. And then this was sort of the baseline when we put the system in. That was just in, well, I guess sort of came online in April of 2018, so just over a year and a half. So, and that's what was allocated for allocations last year. So the expansion basically is one major chunk in red there is we're adding another just under 500 nodes of basically the same node, but it's a slightly newer processor. So the Cascade Lake is just the latest generation. It's not a major generation. It's very similar. 6248 instead of 6148. Still 40 cores per node, same amount of memory. The difference is the clock rate just bumps a little bit, and there's a few little tweaks. They've patched some bugs, and there's a small addition to AVX 512 that they've allowed in there. But primarily, to most users, it's very similar, and it'll be scheduled in very similar ways. So this bumps our total core count up to just over 80,000 cores. So it's sort of a 25% sort of bump on the overall core count we have in the system. So that's about 6.5 racks. One of the features of this, though, is that when we did the other system, EDR InfiniBand was the main one out. Now they have HDR, which is 200 gigs a second instead of 100 gig, and the switches have a higher radix or number of ports. So to expand that Dragonfly topology, we're adding a fifth wing to support all these nodes. From the typical users, you won't even notice any of this, but from a scheduling point of view, it'll try to keep all those jobs together. We will be able to span across if you need to, but from a user joy, you're going to submit your jobs and you're not going to notice the difference. However, there is a slightly different network topology in behind it. That being said, the per node performance is going to be pretty much the same because we're using HDR 100 NICs in the Angel, which is similar to the EDR. The reason for that is this generation of Intel only supports PCI Gen 3, and so there's no real support for HDR 200 on PCI Gen 3. You have to go to PCI Gen 4. So a newer AMD and Power chips will have that. But it's just one of the variations. Most of that is under the hood. You're not going to see the difference. It'll run the same OS, the same software. At the end of the day, you're basically, there's more nodes available. We're getting an expansion on the storage, so we're about another 6 petabytes added onto the spinning disk. So that's more Scratch Project Home. Some of that will be SOSIP. Some of that will be ours expansion on, but it'll be the same. You won't notice the difference. It'll just be expanding it. What's available on that type of thing. One new, sort of complete new feature is we will be adding some GPUs. There'll be a new system added on, 54 of these IBM AC922 Power 9s. These are basically the Summit Sierra Power 9 nodes. They've got 4 GPUs. They're Power 9 processors. The big difference with these ones, or what's unique about that, and I'll talk a little bit later, is that these are not connected through the PCI bus. These use the CAPI or NVLink bus to the CPUs. And to each other, so the internal memory bandwidth space. So those who used GPU systems before, a single GPU would be very similar on the V100, but if you're doing multi-GPU work or a lot of stuff with CPU transfer, this is a different platform again. And these are Power too. Now, so what it means is that you're not going to have exact binary compatibility with your codes that you run on NIAGARA. They'll share the same file system. However, any codes that run on this have to be recompiled, of course, to use that. However, it's designed specifically for GPU systems, so it will be sharing the same file system and everything like this, but it'll be sort of run differently as part of that. Yeah. Yeah. So the good thing about these newer generations is they are little NDN compliant now. So we run the LE versions of everything. So now, like we've used them previously, we run on the Power 6 or the Power 7 or the Blue Gene. You take a file from here and over there, and you couldn't read it without doing a lot of hoop jumping. Now, at least that won't matter. So if you want to process or pre-process, at least from the data point of view, it's the same. The binaries for executables aren't, but at least in this generation now, and it's Red Hat 7.6, so it's very similar. It's just it's going to be in Power. So, and I'll talk a little bit more about how we're set that up. Another major expansion that's already completed is we've added another 36 tape to the HPSS. We haven't had all the tapes in, and we've upgraded the tape library, and that's all up and running right now. So that allows us to expand some more of the storage capacity for Nearline. So that's actually already been completed. Okay. So this was our existing, it's probably getting a little bit of the weeds for some of you guys because it's pretty much hitting, but it's interesting, so I'll put it up anyway. This was the original NIAGARA Dragonfly topology. It was 4 wings, and you can kind of see there's just all-to-all sections. So there's a series of leaf nodes. This is where each individual node hooked up to a series of core switches. And then all these core switches talk to each other. And this is how we make the big Dragonfly topology, which is different than a fat tree where all these would go up to one big master core switch. So in the existing system, we could support endpoints. If you do all the math, it works out to be just over 1,700 100 gig ports that we could support. So that means how many nodes we could hang off that. We're going to be over that, obviously, when we add another 500 nodes plus all the power for us and storage and stuff. So we need to add an extra wing. And one of the things that reason we went with the Dragonfly topology is it has this adaptation by just changing how these blue lines are the top level cables, how they connect to each other. We can add more switches in without having to throw out a whole new core networking or new switches and stuff. We can just restructure it. So the option to do that is we add a fifth wing. And so at those top level switches, we have to change the switching around. This also changes a little bit. Interesting is now with HDR switches, we can still keep the same top level switches, but we add a new row of HDR. HDR, they went from 36 ports to 40 ports, and they're 200 gig ports. So if you use breakout cables, you actually can turn those 200 gig ports to 80 100 gig ports. So that actually, even though we're only adding one new wing, this one new wing can support over 1,100 100 gig nodes. So it's over half of what all four of the other ones can do with full connectivity, inside that section. So we're adding this new wing, and this one new, we only need about a little over 500 for the new equipment. But we'll actually add quite a bit of cross support into that wing. So that's how we're doing that in the back end. So this actually is a fairly cost-efficient way to expand this, and still get within this region. It'll all be HDR in this, and also reduce the number of cables, the number of switches. Right now, in one of our current racks, we have 4 InfiniBand switches for 72 nodes. This new one, we only need 2. So it's a number of cables reduces because you use breakout cables, the number of switches. So that helps with just cost, the overall cost of an expensive. These networks can be quite expensive. They can be 15-20% of the cost of your system is in the networking. Yeah. So the fourth wing is actually being, right now it's about half full. We're using, well, a little over half full, but the storage will be hooked up to the fourth wing because all the existing storage is in there, and also actually all the GPU nodes are going in the fourth wing as well, because the current generation of Power 9 only has EDR support, so there's no point in putting it on the HDR, and it's only 54 nodes. So we will use up most of our existing fourth wing connectivity with that stuff, and the only thing that's sort of right now going in the new HDR wing are the new x86 nodes. So there's just 468 of those new ones, but there's still quite a bit of future expansion. There's no struct reason why we have to do that, but it makes sense because our other DSSGs are all in the fourth wing to keep them all in the same thing. It actually reduces network crosstalk for the ESSs and stuff like that too. And we have those EDR ports. So if going forward, you want to keep the HDR as free as possible for future expansion, right? Because that, when it goes full generation HDR, you'll have that available. So yeah, the NIAGARA, and I said SOS expansion. So this is the GPU system. The naming, it's actually going to be run as sort of a separate system. We're going to call it MIST. That came from a series of iterations. Mike's cringing in the back over there in the corner, but you know, that's the name that fell out. Anyway, it'll run. It'll run like NIAGARA, but it's going to be sort of run as a separate system because it's power, it's GPU. It's kind of got its own dedicated scheduler, but it'll still be Slurm, same file system. It'll be just a different development node you'll log into, same user credentials, all that type of stuff. So even though it's sort of a separate part, it'll still follow all the same accounts and privileges and access that you already have. So these are the little more specifics about it. The AC922, which is the Power 9 nodes. These are 16 core systems, with 32 cores. They have 4 threads each. If you're familiar with Power, there's various variations on the old Power 7. They had 8 and they had 2. These are a 4-threaded version. They have CAPI enabled on them. This is their IBM specific, only IBM, but it's their high performance bus. If you're familiar with the GPUs, this is the NVLink. This is instead of going through the PCI bus, this allows the memory bandwidth to be much closer. These are PCI Gen 4 and they're EDR InfiniBand, and they're running Red Hat. We have 3 of these up and running right now. We're just building the software stack out. And there's a few features that we'll get into more details about, some of the idiosyncrasies of them and how they're different to say what you would run on say a newer system like Beluga, which also has Volta GPUs. These are the 32 gig versions, but if you see this SF, they have a NVLink as well, but these ones are connected right to the CPU. So there's a few different variations, and that may change applications and how they work. So the software and configurations, it'll have the same module system you're used to. Of course, there'll be different modules. In this case, there's no Intel compiler, obviously. It'll have the IBM compilers. GCC OpenMPI will be the standard that you're familiar with, but then I'll also have some Spectrum MPI and some of the IBM specific stuff as well. Share the same file system, Slurm schedule, mostly it'll be fairly straightforward. The main goal right now that we're working on is, because there's only 54 nodes, and for certain reasons, you can obviously schedule before full node, and then you'll get all 4 cores, but we'll also be able to schedule per single GPU. And that should help some throughput for certain jobs, because a lot of GPU jobs don't have that parallel capability. That's still sort of a work in progress, and there's some technical reasons why we want to do a certain way and how we partition menu. But once we get that up into production, the wiki will have a fully, and we'll probably do a specific intro to MIST in one of these sections specifically about how you submit jobs, how you run it, what you should look out for, performance differences. So if anybody involved in GPU work on any of the existing systems, let's say Graham or Cedar or Beluga, and you come over here, obviously it's got to be ported, or your application has to run on power, and then also there's some different performance characteristics, even though it's similar. I mean, it's a different architecture, but it's also, even as the same GPU, how it handles memory and transfers could be different on the system as well, too. Okay. Yeah, so this is one of the documents that we'll pull up here, and we'll get into a little more details later, but this is just something to think about and how they're different. On an x86 system, even if the GPUs they're PCIe generated themselves, some of them, and like say a DGX type thing, you can have up to 8 GPUs talk to each other with these different NV links, and the links are 50 gigs a second, so you get all these different cross sections here. How they're done in the Power 9 is they bonded a bunch of these links together, and so there's 8 links total, and they use the sort of these 2 GPUs to each other and then to the CPU. And so you get this very sort of balanced approach is what they're going for. But as you see, it's not balanced across all 4 nodes or all 4 GPUs. And so this is something to we'll have to be aware of when you're running. That's why how we schedule it will matter too, because you don't want to end up with one part of your GPU job here and one part of your GPU job there, right? So this should really help jobs that have a lot of memory transfer. I mean, that's the whole idea. It's much more balanced. You get a lot more to the CPU than you do through a PCI Gen connection. But a lot of the framework should take handle this. It's a difference. It's a part of using that IBM platform is it should get set sort of a native platform. This also, the Power 9 and the IBM have really put a lot of work into the OpenMP 4.5 and 5 standard for offloading as well too. So if you have a threaded code and you want to do some offloading, you can actually do that through the compiler, and if you don't have a CUDA code, you can actually offload there. It has some various sort of complicated memory architecture too, about where it can copy and where you can even direct access, the OS can direct access the memory too. It's not as hidden as a unified memory as you'd like, but there are some features there that you don't currently have in the x86 world as of yet. So these are, and this can lead to some good performance work depending on the workload you're doing. If you're just doing some heavy GPU only work, that's 100% on the GPU, it's not going to matter much. But if you're doing a lot of transfer back and forth or some large GPU jobs, then some of these features will come in handy. So I just mentioned them here. I'm not going to get into full details without, there's a link here if you want to follow it up to do a lot more in-depth reading if you are investigating this, or maybe you've run on a system like Beluga and you're like, well, why do I get different performance with here than there? There is sort of a difference, even though the chips are all Volta chips, how they interact with the host operating system and transferring data, and then transferring data from there to another complete node through the network can make a big difference, especially for scale up. It's no different than scaling out of a CPU. It's just now you have more levels of hierarchy. So that's why I pointed out here is it's one of the key sort of differentiators of this type of system. And if you can leverage it properly for your workloads, you'll get some decent speed ups that you may not get on one of the other systems. For Compute Canada, sort of the division is 16 of these are Compute Canada systems, so that's available. The other 34 are SOSIP. So those will be sort of the ones that are ours, or that's the part of it will be available for those type of jobs. Obviously, they'll be in the same scheduler, but just in terms of bookkeeping, that's That's the portion of the system. Also from the x86 system, the SOSIP's portion of that is one of the racks, so 72 nodes, so just under 3,000 cores of the x86 as well too. So for those that have SOSIP allocations, that's their portion. Anyway, I think that's. Did I have anything else? Oh, these are just old pictures because I didn't have any new pictures. That's the original management rack. You can see on the far corner here. These are the 3 racks of InfiniBand. As you can notice in these spacers, we actually left, there's another picture I think that shows better, spaces so we can actually drop in the InfiniBand switches right in there. Currently, there's 18 groups of 4 switches. It'll go to 18 groups of 5 switches. The rest of that's just storage. This is one of the storage racks. Currently, we have 3 of these. We'll go to 5 of those. Yeah, so there's the back end rows. You can see there's 2 spaces in here. As long as you're not the guy running the cables, but the cables we don't have to move. The blue cables are the fiber optics, those uplinked to the racks. The ones that we need to modify are these short, only half a meter or 3/4 of a meter copper cables. So we will have some downtime. Probably it'll happen just in like January or sometime, where we'll have to take a day downtime to rewire those switches to get the new stuff up and running. But it allows us to reuse all the existing stuff. So from a cost perspective, it's actually a fairly efficient way to do things. Yeah, so no, that's the currently we're sitting at about 22 racks on the x86. These are the x86 NIAGARA nodes. So that's NIAGARA. We'll be adding another 6 of those, another 4 GPUs. So it's a little bigger physically, but more of the same. So it's not a huge expansion. And we were hoping to almost double the system, but because of the way the funding works in the Ontario government and the funding that we have right now, this is the money we have to work with. We've leveraged the SOSIP money as well. I think it'll work good for them and as well as the Compute Canada users to have one single system. And so now we'll have 2. We'll have the GPU, but we won't have all the different compartments. Whereas those who are familiar with the Blue Gene before, it was sort of a standalone system. Now it'll be a little more tightly integrated. So if you do want to do workloads, so you're running a regular simulation and then you wanted to do some AI or some post-processing with the GPU system, you don't have to transfer that data. You can do that all within the same sort of framework by just submitting another job. So I think that'll make it easier from an administration point, software stack, and as well as from a user's point of view. Okay. So that was just a quick overview. As I said, the system we're still putting the hardware in now. It's going to be a few months before it's up and running, but it will be fully operational for the next rack coming up. So April of 2020, I guess, we'll be able to allocate those extra cores. But in the meantime, in the spring, there should be a few more to use. Well, for the last couple of months of this existing rack, which is never a bad thing, right? But, okay, so I think I'll open the floor to questions, I guess. You guys have any questions about the hardware or how we're going to operate it or what's going on in the other systems or anything? Okay, I guess we can just, that's all I really had. I know it wasn't super long, but that was wasn't much stuck there. But if you have other questions too, this is a user group meeting, so feel free to bring up any other questions or things you want to talk about. Sorry? So the CPUs will be allocated, just there'll be more of them available. It doesn't change anything, just instead of us allocating whatever 80% of 60,000, it'll be 80% of 80,000 or whatever that portion is. The GPU portion, I think at least for the 2020, those 16 at Compute Canada, they're not going to be allocated as part of the rack. They're keeping them separate because it's a small partition, and we have some requirements under it to actually, there's some details to that, but basically show that we're getting users to use the GPUs. So they'll be basically, the GPUs will effectively all be default. There may be a few small partitions in there, but basically they'll be up for grabs. So it's a really good boon for if you're a GPU person who doesn't have an allocation. That system will be a good place to scavenge resources on, because it's not like it's 90% are going to be allocated to project XYZ. It's not a huge amount, with 16 nodes, but for those that are sort of developing code, want to try something different, or have some smaller resource demands, especially if anybody's run on the other systems, the GPUs are highly oversubscribed. It's a good place to do. Now, what happens after 2020? It may be allocated after that, but at least we're keeping it free for that first year for people to go ahead and use it as a sandbox type of thing. The 34 that belong to SOSIP, that's, I don't know how they'll be allocated. That's up to them. I don't know how that projects will be allocated. Same with their resources in there. But at least from the portion that we're going to keep in the sort of Compute Canada open, they'll be free to use. You can just consider them more default available.
That was the CC thing. Are those also the Volta? Or?
Yeah, the system's all the same. It's 54 node. Those are exactly the same. We bought the whole point of this is to buy exactly the same hardware. It's just allocation. It's just like if your project you put in a rack allocation, you got 10 and somebody got 20. All we're doing is we're just hard carving out they'll get a prefixed allocation for SOSIP. And if you're a SOSIP user and you're a CC account, you would just change your account that you would account it towards. And if there are no SOSIP jobs in, then 54 nodes are available for anybody to use. That's the whole point. I mean, we're putting it all together so it's not hard partitioned. They're a flexible, larger pool of resources that can shift one way or the other. And that's the idea, right? So they're all the same hardware, same software. This is just a pooling of resources, and we'll do the bookkeeping just to make sure everybody gets their allocation that they paid for. But other than that, we already have added some nodes. Like right now, originally we were 60,000 cores. Now we're about just under 62, and that's because if your professor has a gel for something, they can add resources on, and then we just give them a fixed allocation of those 10 nodes. But to a user, there's just a pool of more resources. We tend to like to do that, so then it's just more of the same. So yeah, they're all the 54 nodes are exactly they're just a pool of resources. They're all exactly the same. So if you did have say you want to do a scale up job, and you're like, oh, I'd really like to see how GPUs scale across 50 nodes, we can do that. There's nothing stopping besides a Slurm parameter to allow a user to say, I want to run a scale-up job, and that's totally doable and actually advisable. That's the whole point of pooling them together on one big network is so if you want to do a 200 GPU job for, not forever, but for a testing or to see if something works well, this gives us the capability to do that without having to partition it. What do you mean in terms of? Oh, well, no, when we say we allocate it, so they will be allocated, but not, so you'll submit jobs like you normally do, and you'll you'll request GPUs, so it'll be either 1 or 4 GPUs, right? And you will. What I'm talking about is the rack won't allocate them. They'll still be scheduled by user jobs, but we won't. So normally how the current system is depending on which group you're in, you get different priority based on which allocation system you're in. So we're saying those 16, everybody's got the same allocation effectively, at least as a ballpark. So yes, that's from a priority point of view or a fair share point of view. From a resource point of view, yes, you'll still submit a job. I want 3 nodes with 4 GPUs each for 10 hours because that's to schedule it. But if you do that and the guy from the lab beside you does the same thing, you'll have the same priority, right? There may be a little bit of that we'll mess around with, but at least on the NIAGARA system right now, last year right now 94% of it was allocated to rack allocations. So if you don't have one of those allocations, it's much tougher for you to get jobs in, just because of the throughput.
What is
Sorry.
What is
It's a year. So the racks are come out. So this next one that is just closed, if your PIs have already supervisors have put an allocation, they get reviewed now, and then they whatever allocation they picked for the 2020 starts April 1st, and it runs through the next. That's the April to April timeline. So the 2018-19 started in April, is active right now, and will go until that one. And so that's where. So there'll be a bit of a gap there. We allocated 54,000 core years last year, and if we have the new system up and running with those extra cores, there'll be a bit of a burst of free zone because we have a few more resources available in, say, March, so that people can scavenge on them for that time period.